All right, so it's now 3:03. I think we'll get started. Today we're going to be talking a lot more in depth about natural language processing and how we can use neural networks to solve this really big problem. You might remember that we talked a lot about this yesterday when we discussed recurrent neural networks, but everything I talked about was in super vague terms. I was saying things like, just imagine that a word can be represented as a number and we'll just feed it into this neural network. And then remember, yesterday we talked about recurrent neural networks, where these things, um, these uh, these these inputs, where we just assume that they were numbers like x's. We were just feeding them again and again into this model, and the model was trying to remember something about this input, and then it was just going to keep going again and again until you reach the end of the input. But the key assumption that we made was that you can actually represent words as numbers, right? We said that the dog was blah, 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 or something like that. And this isn't so intuitive, right? Because words, there are so many different words, many, many words in the English language. And then if you think about all different languages, there's just a very, very vast number of different combinations of characters that could be valid, that could have meaning. So today we're going to be discussing some ways that computer scientists have used to overcome this problem and represent words in a manner that computers can understand and that we can do math with. So that's going to be the whole thing with today. But before we actually talk about the math, I just wanted to point out a couple of observations about language that make it so interesting and that make natural language processing itself so hard. Because for one, when you look at text and you don't listen to someone say something, you lose the verbal aspect of it. There's a little bit of information lost, and the way that these five sentences are structured really shows that. Because if you read these sentences out loud to yourself and you emphasize different words in the sentence, you'll notice that all of these sentences mean different things. If you say, I never said you did that, well, that means maybe I didn't say that, but someone else did, and I agree with them implicitly. I never said you did that. Maybe I never said so. I might have thought that you did that or might have agreed implicitly that you did that, but I never said it explicitly, et cetera, et cetera. So there's a great deal of uncertainty when you're dealing with language. And there are just so many nuances, not only of the English language, but also of different languages out there that it makes NLP a very, very difficult task to tackle. And of course, humans, when they construct sentences, they're not always thinking about 100% of the considerations that you can make. And all three of these examples show that, where there is some ambiguity left in the sentence. And you can see that um, these bullet points here point out some of the questions that you might ask. So clearly, the language or English language, or we'll just consider English for now. Of course, what I'm speaking about generally applies to all the different other languages. Language is an imperfect sort of compression of ideas. You take your ideas that you're trying to formulate in your brain, and then you sort of abstract them, you compress them down into a form in which you can actually communicate and verbally or in writing communicate. And so there's a lot of information lost. That's sort of the point here. And there are a lot of challenges that we need to deal with because humans writing English, they're not always perfect at doing it. And this makes deciphering their meaning all the more difficult. Now, of course, finally, there's also this consideration that you have to think about, which are illusions. Um, Different people say things in different ways. You've all heard of idioms or slang. These are all things that are non-standard, things that you, or phrases that you cannot interpret literally, that they have some kind of maybe cultural or historical background that make them more significant than the components themselves. So this is another thing. If you really want to understand language, you truly need to understand the culture of the people who are speaking this language. So in America, this would help you understand, the slang that people use or the allusions that people like to make. They're, so to say, inside jokes. And as a result, when we think about building NLP systems, we not only have to think about the literal syntactic and semantic meaning of things, but we also have to have this sort of understanding of the world, so to say, where you understand the context behind all of the usages of all these terms. So these are all just a whole slew of different problems that make NLP so difficult. And putting these together, you get some of these common NLP tasks that people like to talk about. Some of these are pretty easy. Maybe, they're still generally hard, but deep learning has solved some of these pretty reliably. One of them is sentiment analysis. So we talked about this a little bit yesterday, or you're given a sentence and you try to classify it into certain classes. It could be sentiment, whether the sentence is saying something positive or negative about a certain entity. It can be polarity, whether the sentence actually provides a really, really strong opinion or whether it's fairly neutral, fairly weak. You might think about spam classification. We talked about this earlier. So if somebody emails you and says, if you pay me 2,000, I'll double it up and give you back 4,000 because I'm feeling generous, then you might know that this is a spam email. So this is another thing that we use language to attack. You just read the email and you should be able to know whether it's spam or not. Or there's this problem of part of speech tagging. This could be very important in a variety of different applications, but how do you take a sentence and assign part of speech to each one? This is a verb, this is an adjective, this is a noun. And this actually is a little bit more difficult than you might think because certain words can take on different forms. I can't think of an example off the top of my head, but certain words can act as both nouns and verbs, for example, and that makes things a little bit more difficult for computers. So these are the tasks that deep learning has solved pretty well, but there are other ones where we're having a lot of difficulty. You might think of things like question generation. So if you gave it a wiki article, about maybe Albert Einstein or something, and you feed it into this model, the goal is that you can generate some questions that maybe test a user. So you might think that this is useful for studying for a test. Maybe you're talking about the immune system. You just look up the wiki article for it, and then you can use the computer to generate quiz questions for yourself based on the contents of the article. Some people have looked at generating natural language, like free response questions, or there's a lot of research going into generating multiple choice questions. And so in generating multiple choice questions, you need to think about a lot of different interesting things. For example, you need to put the answer in here, like that's the obvious part, but you also have to create good distractors. If A is the correct answer, B, C, and D cannot be too wildly, irrelevant. If you're talking about the immune system, you don't want B, C, and D to be talking about bananas or something like that. So a very difficult thing that people have not really feel like they've cracked yet. Stance detection is another difficult one that I'm actually working on, which is given two pieces of text, do they agree or do they disagree? This is of particular interest in fact-checking circles where, some dude on the internet, maybe on Twitter, they tweet, and they claim something. For example, a politician might claim that, oh, America has has its lowest unemployment rate in 50 years. And so you have this tweet, and then you have some evidence. So these are just two sort of text documents. They got a bunch of text, and you want to put them both into a model, and you want to know whether they agree, disagree, or et cetera. It might be discuss, or it might be, they're completely irrelevant. But so if you notice, if we can assume that our evidence is actually correct, this is a strong assumption to make, but let's assume that our evidence is generally reliable. We've gathered it from a source that is quite responsible in its reporting. Then if the evidence agrees with the tweet, then this tweet is probably more likely than not going to be true. If the evidence disagrees with the tweet, assuming that the evidence is good, then the tweet is more likely than not to be untrue. And so this actually is a key part of a lot of computational fact-checking systems. And so this is of great importance to our society, I think, at this moment. And it's actually quite difficult to do. People have not really done a good job with this. Translation, you might know that Google Translate, translates between different languages. It works okay. It doesn't really pick up on some of the nuances. For example, if you try to translate Chinese to English or English to Chinese, but it does a fairly decent job. But it still is, I would consider, a really, really difficult problem because of the nuances of different languages and how they might intermesh. And then finally, there's this problem of bots. You might notice that when you talk to maybe an automated assistant over the phone when you call in to a company. Uh, the automated bots are pretty dumb. It's very difficult for them to really understand what you're looking for because they've just been hard coded to follow some rules. And so building bots that feel like they're sentient and feel like you can converse with is very, very difficult. We're starting to get there with technologies like GPT-3, which is an autoregressive model that we'll be talking about today that can generate text, that can generate text given a prompt. And so basically your prompt would be whatever you try to say to it, and then it would generate a response to your prompt. So we're getting close. GPT is actually pretty good at generating text that people cannot decipher between human and non-human. Uh, but if you read closely, you can still sort of tell that GPT is just spitting out words and not really saying anything at certain times. So hopefully this gives you a good idea of some of the problems that are of interest to people in NLP. When you first start out, you're probably going to interface with these the most. I think all of these can be treated as classification tasks, so they're a little bit more straightforward. And then these are just like very difficult that people have been trying to solve, and they made good progress with deep learning, but still a little bit difficult to do. And I would say that we talked about yesterday, image captioning falls under this category. It is quite difficult to do image captioning. But as we will see today, this is actually going to be our lab project. It does a pretty good job. It's actually pretty good. So hopefully this gives you a good idea of the problems that are of interest to people in NLP. All right, so we've talked about all the tasks in NLP, and sort of the natural question now is, what are people doing to solve these tasks? So it's quite simple. This is the model of neural NLP basically that everyone uses today. If you forget everything I tell you today, this is the slide to remember. If you forget everything else, this is what you should take away, because as long as you understand this, then you will be able to have a general intuition for how pretty much any NLP model works out there. And I think this is pretty powerful. So let's dive in. At the very beginning, of course, you have a bunch of input sentences. This is natural, just like, you got a bunch of sentences. And let's just roll with the case of sentiment detection on reviews. So if you think about on Amazon, people leave reviews of items and say that you are Amazon and you want to figure out really how positive are these reviews, how negative are they, and just imagine that the star system doesn't work. Like there's no 4.5 stars, 4.7 stars. You're just trying to gauge it specifically on the text, which might contain more accurate information, because perhaps bots can go mark the stars. Sometimes people mark the stars for no reason, and the people who are actually speaking out on things probably are probably more representative of the quality of the product. I'm just assume that this is the case. So we have a bunch of Amazon reviews. Of course, you want to put them into a data set, and you put them as an input sentence. Then you pass it through what is called an encoder. So as the name might suggest, an encoder takes all of these sentences and it encodes it into a certain representation. We call this an encoded representation. And the key word here is that it's an abstract representation. What does this mean? Well, you take an input sentence, like you might think that this, maybe you bought an MP3 player. So this MP3 player was awful. Maybe we had a really bad product. And you put it through an encoder, and this is basically just going to give you an array of numbers. It's going to give you like just a bunch of numbers. These are all on the real number line. So this is just a list of real numbers. And this might seem really confusing to you at first, but remember, what did we talk about yesterday? We have an RNN that takes in a bunch of these inputs, say that this is our sentence, then we put them all into the RNN, and this RNN is like processing it all here and here and here. This hidden state, H1, H2, all the way down to H5, these are all actually, this is actually the H. So H of T, or any H, just looks like a list of numbers. Yesterday, we operated with just one number to make things simpler, but in implementation, this is actually a list of numbers. So what does this mean? Well, these numbers on their own, to the human eye, they don't mean anything. But to the computer, this is actually the memory that we were talking about yesterday. This H5 that we get out here, which is just a list of numbers, it actually represents everything that the model thinks is important about the sentence. So at H1, it might not know anything. At H2, it knows that we're talking about an MP3 related thing. At H3, it knows that we're talking about a player that plays MP3 players. H4 doesn't really help much because was is a helper verb, I believe. And then H5 is awful. And so finally, if you put everything together at H5, our list of numbers will show the computer will look at this list of numbers and it'll be like, ah, okay, so this sentence is about some dude who's complaining about some object that plays MP3 files and it was a trash product. So this is what we call the encoding. And why do we call it the encoding? Well, we've taken this signal. This signal is just a list of words, and we have encoded it into a more abstract representation. We've encoded it into a list of numbers that we don't understand necessarily, but the computer understands it. The encoding for computer. And this is the most important part. The computer understands it. It doesn't matter that we don't understand it. The computer knows what it is. So this is what we call the abstract representation. So once you have the encoding, you have all of the information in the sentence. You know exactly what's happening in the sentence. Here, there's a dude complaining about a really bad MP3 player. And so now you can do anything you want with this representation. Usually there are one of two paths that you choose. You either put it through a fully connected layer or you put it through a decoder. If you notice, remember from yesterday, the fully connected layer is exactly what we do when we have when we want to do classification. Yesterday, we were talking about toxicity detection. And today we're talking about sentiment analysis on reviews. But your fully connected layer will give you a set of classifications, right? And all of these are all classification problems. I won't talk specifically about these, just know that they exist, NLI and textual entailment. Don't worry too much about what those mean. But here, it's very obvious, right? We're trying to do spam detection. So this is a classification of yes or no. Toxicity analysis, yes or no. Bias detection, it's sort of like yes or no. Fake news detection, yes or no. So as you can see, when you put it through a fully connected layer, you get all of these classifications out. And they use this encoding of the sentence. The computer understands what's happening. And then you apply a fully connected layer. It's just a dense layer. And you'll get out a result that tells you the classification that you want. So that's great. The other thing that you can do is you can put it through a decoder. You can look at the sentence. You can look at this abstract representation, this list of numbers that explains to the computer what's happening. And you can say, well, let's try to decode this sequence. And your decoder is another neural network, and it might do a bunch of different things. But the whole key is that decoders are good at generation because it can do translation. There are models that can actually do playwriting, which is some people have made models to emulate the style of Shakespeare or something like that. And finally, you can also do image captioning. So decoders are typically for X to many, where X could be either one. It's either like one or many. So it's either one to many or many to many. This is when we use a decoder for the abstract representation. And then usually for fully connected, it sort of depends, but usually this is for anything to one. So hopefully this gives you a better idea for how neural NLP works. Just as a recap, pretty much always you'll get an input, you'll encode it, which means you'll put it into a form that the computer can understand, this abstract representation, and then you can do anything you want with this representation. You can do classification or you can generate a bunch of text. And we'll see exactly how this works in a moment. All right. So now that we have a good idea for how NLP is structured and what the tasks are and what the general framework for solving it is, let's think back to some of the earlier topics that we covered, right? So we talked about artificial neural networks, which can take in a bunch of numbers. We have KNN, which you plot the data on two axes as a bunch of numbers. We did regression, where you plot the data on two axes as a bunch of numbers. And then this is something we didn't talk about. This is a support vector machine, but it also takes in a bunch of numbers. So the common denominator here is that you need numbers. You need numbers to do machine learning. And unfortunately, words are not represented well with numbers. And this is a big problem because all of our machine learning is centered around this problem of finding mathematical ways to model things in our world. So how do we fix this? Well, there is one way that we can fix this. I'll sort of try to draw out the actual solution just by starting from the most intuitive way, the most naive way of doing things, and then progressing up further and further. But one way that you might think of this to do this is to make is this is like the dumbest way that you could probably do it. You have an array, right? You have a whole set of words. Let's say that the English language has, I don't really know how many words are in the English language, but let's say that we want to consider 10,000 words in the English language. This is not all the words in the English language, I don't think. But let's say that we want to do modeling on 10,000 words, which is a subset of the English language. And how we could turn this into a number is simply construct a big, big matrix. So we could say that a big matrix, and this matrix has 1,000 rows, and and um, and let's say it's 1,000 by 1,000. And basically, what you would do is every word is represented by by a list of numbers that has exactly 1 and everything else is 0. So what does this mean? So say that we simplify this down, and let's say that this should be 10,000, but 10,000 is a big number. Let's just say that we consider 5 words. So we might have 5 words. You would have maybe the, is, was, from, he, these 5 words. And each of these 5 words would be represented by a different list. So the would be represented by 1, 0, 0, 0, 0. Is would be represented by 0, 1, 0, 0, 0. Was would be 0, 0, 1, 0, 0. From 0, 0, 0, 1, 0. And then finally, this one is everything, and on the last one. And what does this do for you? Well, then you could take the, and then the would be converted into a number that looks like 1, 0, 0, 0, 0. And then what would is look like? It would look like this, and so on and so forth. What you can do then is you can treat this as the input to your recurrent neural network at each step. And we'll do some review on recurrent neural networks in a second. But remember that basically this is like a neural network. So you have a neural network with 5 neurons, and you would put in 1, 0, 0, 0, 0 for the values. And then you would just run it through the neural network. You have a neural network here that has a fully connected layer. Everything's connected to everything. And this would be your input, 1, 0, 0, 0, 0. And what's nice about this is that the representation is super simple, right? And you could code this up really easily. This is literally just an identity matrix. You have the 1, 0, 0, 0. So every single word is different from every single word, of course, because you can convince yourself of this by saying, well, the first index will only ever be 1 with the, and all of them else will be 0, and so on and so forth. So the cannot be the same as the others. Then this one will only ever be 1 when the word is, and so therefore is cannot be the same as anything else. You just keep running this argument again and again, and you'll convince yourself that everything here has a distinct representation. So this is a super easy way of doing it. What's bad about this though? Well, first of all, I guess I should introduce the official lingo. This is called a one-hot encoding. One-hot meaning that there's only one element that's, let's say, interesting. There's only one element that's interesting to us, and that's the one element that has a 1, because everything else is a 0. So words can be represented as one-hot vectors, where you have, this one says that there's 120,000 words in the dictionary, and everything is 0 except for this one index that corresponds to motel. Or everything is 0 except for this one index that corresponds to hotel. Unfortunately, this is not such a great representation. There are some problems with it. And one of them is this problem of orthogonality. I think this is just an awful word for introductions. I think it's much more easy to say perpendicular. Actually, I don't know if this is any more clarifying. But the problem is that, okay, I don't know if I should explain this. Well, yeah, let's just go for it. So
The
if you
product is zero.
right. But it's not easy to motivate what this means. Let's just put it this way. So imagine that these lists of numbers are vectors, right? They're just arrows pointing out in space. The problem with this is that all of these vectors, because there's only a 1 in this location and zeros everywhere else, every single vector, every single word is what we call orthogonal to every other word, which means that if you plotted this out in 120,000 dimensional space, these two vectors would be perpendicular. And what's the problem with this? Well, when they're perpendicular, you can't really tell how they're situated with respect to each other. Because if you had two vectors that were sort of not perpendicular, they were at an acute angle, then you could basically say, well, these vectors are in a very similar direction. They're sort of both going this way. And there wouldn't be orthogonal, they'd be almost parallel. These are almost parallel. And in the other extreme case, where you have two vectors that are very not acute, this is a huge obtuse angle, then you could say that these two vectors are very, very different. They're pointing in almost opposite directions. And then, so of course, the other extreme is when they're exactly 90 degrees from each other. This is a right angle. And you would say that these two vectors are, are orthogonal. And this isn't super interesting because you can't really tell whether they're in agreement or in disagreement. They're sort of just sitting there next to each other, and there's no measure of similarity. And so this is in the two-dimensional case. When you get into 100,000 dimensional space, vectors are very, very often orthogonal. And it happens to be that the representation that we chose here, this one hot encoding, is awful because every single vector will be orthogonal to every other single vector. So there is no natural notion of similarity. All of these vectors are all neutrally sitting perpendicular to each other. None of them are super in agreement and none of them are super in disagreement. What is the problem with this? Well, if you think about this example that we have here, in web searching, motel and hotel are actually very similar words. If we wanted an ideal representation, ideally these two vectors would be pointing in a very similar direction. Why? Because they're similar words, right? Motel is basically a cheaper, maybe shorter term version of a hotel. They're both places where you're supposed to sleep, eat, and get your rest in before you move on to your next day. So these are very similar concepts that they should not be orthogonal. Their dot product or their similarity should be very high. And unfortunately, one hot vectors do not capture this relationship, and so they're bad. So we want a better solution. And as with everything in machine learning, usually when we find a problem with the representation, we just think, so computers, they're very fast, they can look through lots of data, and by looking through lots of data, they can become smarter than we are. So why don't we just use machine learning to learn these vectors? So instead of enforcing the property that all of these have to be, um, all zeros except for this one element here, let's try to learn a representation. This is literally just the whole. This is this is a perfect. This is a perfect machine learning task because humans are like, it's too difficult to design vectors ourselves, so we'll just ask a computer to figure it out for us. So the fundamental idea behind this is what we call distributional semantics. It's a little bit of a very fancy word that doesn't really mean much. It's a very simple idea. And I think this captures it pretty well. You shall know a word by the company that it keeps. And this is this is basically the foundation for much of modern NLP, which is representing words by their context. So let's try to figure out what this means. To build up our intuition, we should look at this example here, where if you wanted to construct a vector for a certain word, right? We think about the word banking. Banking has lots of different sort of meanings. Banking can obviously mean the institutions that manage our money. Banking can also be, or a bank can be, the bank of a river, the sort of piece of land that's next to a river. Banking can also be a verb, because banking, when you're sort of banking on something to happen, that means that you want this thing to happen and you're sort of relying on it. There's also banking, which means that something is not flat. A plane can be banking left if it looks like this, or banking right if it looks like that. So there are a whole lot of meanings of banking. And the way that we represent banking should be determined by the words that come next to it. For example, this banking is clearly we clearly know that this banking is of the form of the financial institution, because we're talking about regulation. There's a whole lot of talk about regulating banks. India has given it its banking system, a system. None of the other definitions of banking fit a system, I don't think. A banking crisis. We already know what happened this in the financial crash, 2009, 2008, government debt. So all of these context clues can tell us that banking indeed is um, is the is referring to the institution, the money management institution. So this is the fundamental idea that will allow us to train our word vectors. And this is going to be a very powerful idea. But before we talk about how they're trained, I just wanted to show the result of training. So once you do a bunch of this stuff, you use distributional semantics to train your word vectors. Let's look at what they would look like. So again, this is what they would look like. In deep learning, you will see a lot of this. You'll see just a bunch of arbitrary looking numbers that don't mean anything to you, but they mean something very significant to the computer. So this is an example word embedding for banking. It is just a bunch of numbers. This could be an n-dimensional space, but usually in large models, this could be about 768 dimensions. This is the dimensionality in BERT. Or even in huger models like GPT, this is 1600 dimensions. So this is a lot of memory. Every single word is going to be represented as a list of, say, like 1600 numbers. Every single one of these means something significant to the model. So what these are called, they're called word vectors. They're also alternatively called word embeddings or word representations. And there are some very, very interesting properties about these things that we should take a look at. So this is a visualization of a word vector. Now you might notice that this is actually 1, 2, 3, 4, 5, 6. This is in 9-dimensional space, but we've compressed the representation into 2 dimensions, probably using some dimensionality reduction method like PCA or T at SNE. But this is the sort of idea. If you take these word vectors that you train with a machine learning model, you will see that they follow some very interesting patterns. If you just take a look at this, you can see that all of these helper verbs, I think all of these helper verbs are all in the same area. They cluster over here. And then you see that all of these things that are sort of verbs that describe human thought or human emotion, like maybe a human would say something, human would think, they would want, they would expect, they would see. All of these verbs, they're all clustered around here. And so in general, you can see that once we train these word vectors, there is a hugely improved sense of similarity, a notion of similarity to these word vectors. Like these vectors, if let's say that this is the origin, they're all very, very well aligned with each other. The dot product between all of these vectors is going to be super high similarity. On the other hand, this would have a pretty low dot product with these. This would be low similarity, because these helper verbs do not really have much similarity with these verbs that describe the human condition, or whatever you might call it. But on the other hand, these words, these vectors, they're all very well aligned, and this is another high similarity. So there are these nice properties of word vectors that help capture its meaning in the language. As you can see, we're capturing meaning not only based on what these words mean, but we're capturing them based on their structure, because these are all function as helper verbs. So this model has implicitly learned some idea of grammar, which is pretty amazing. All of these verbs are clustered together. They all focus on the idea of the human thought process, the human condition, the human things that go on inside your head. And so this is not only a syntactic thing, this is also semantic. Uh, so not only based on grammar, but this also captures some sort of meaning of the word. You can see that these mean very different things from these things. So these are a much, much better representation for words, much, much better than this really bad way of representing words that was simply just stacking in 120,000 zeros minus one and then a single one in there, because all of those would be pointing in orthogonal directions, and you can't really tell how similar they are. So in addition to this property, there are also a lot of different interesting properties of word vectors. This one I think is pretty fascinating. So if you took word vectors of the king, a man, a queen, and a woman, and you can do math with vectors, right? I'm not sure if we have learned how to do math with vectors, but the idea is if you want to add vectors, you just take this vector and this vector, you would move this vector over here. It would look like this. And then this new vector would be the sum of those two vectors. But even if you don't know how to add and subtract vectors, just roll with me here. If you take king, some vector for king, and you subtract the man component out of it, and then you add a woman component out of it, you will get a queen vector, which I think is really fascinating because the model was not trained to do this. It was trained to do a specific task that we'll talk about in a second. But by doing gradient descent, by doing backpropagation with recurrent neural networks, simply just by learning a very arbitrary task, we were able to find this kind of relationship. So again, whatever the word thinks, are the abstract representation for king, and then you take the abstract representation for man and you subtract it out of the king vector, then you add the woman. Basically, you're switching the gender of this entity. You can get it to be queen, which again, I think is very cool. And this is one of the nice properties of word vectors. You can do nice math with them. And there are also a bunch of other different ways that this manifests. For example, all of these vectors, right? They're all very similar. All of these vectors from the left to the right. Well, if you look at how they're positioned with relationship to these words, you have a country and its capital, and this vector here sort of represents the direction from the country to the capital. So you would see that if you just took, so the implication of this is that if you took any country and you knew what this vector was, let's say that this country to capital, this country to capital vector v, if you took any country, so any country vector, and then you added v to it, and then you take them for you reverse engineer their embedding, you might take the nearest neighbor or something, then you get the capital vector. So what does this mean? This means that V encodes the information that allows you to get from country to capital. It encodes this relational fact. And that's super cool because then word embeddings can be used to memorize facts, right? If you deleted all of this information, you could recover it simply by knowing what this vector V was and also the vector of the country, which I think is super cool. All right. So does anyone have any questions about what we covered so far? Any questions about maybe confusing parts of what vectors are and how they relate to words, or how words are converted into math? Or if you're good, then just throw a thumbs up into the as a reaction.
So this distribution on this map, right? They are created by the contents that you input into the artificial intelligence model, right? If I take another bunch of information, that will give another map like this or not?
Yeah, so this is actually computed by training over a data set. I haven't explained what it is yet, but I will in just a moment. But it's actually quite a dumb task. I'll explain it very briefly here. If you have a sentence, the man is walking, what we do for pre-training these word embeddings is we take the sentence and we delete one of the words. For example, we will delete the word walking. And what happens is we ask the model to predict the next word. We show it the man is, and we ask it to predict walking. And by doing this again and again over all of the different words, sentences on the internet, you might think that we download all the news articles, we download all of Reddit, we download all of Facebook posts or things like that, and you run this procedure on all of them, trying to predict the next word. It happens to be that this is a very good task for learning a strong prior for the task of language modeling. Or what this means in more general terms is it learns a very good word embedding representation for words. So this is why I said that word embeddings were so fascinating, that you give it this very seemingly arbitrary task. This is called an n-gram prediction, where n is the number of words that you show it. I think this would either be a 3 or a 4 gram. Um, you show it these words and you ask it to predict the next word. And in learning to do this, it learns a very fascinating representation of the English language that we can use as word embeddings. And this produces really good uh, priors for downstream tasks, which I think is quite cool. Does that answer the question?
Thank you.
All right. There's also another question. Could you go over the conversion one more time? Um, would you mind clarifying what conversion you're speaking about? Is it the converting from words to math? Yeah, sure. Okay. Yeah, I can do that. Um, the whole idea here is that we want to make a mapping, right? We want to have a function that takes in some word and outputs a vector. Are you good on what a vector is? Sort of just a list of numbers that represent the direction in space. Okay, vaguely. So don't worry too much about what this is. I think the intuitive way of thinking about it is on the 2D plane, where a vector is just an arrow that's pointing somewhere. But don't worry about too much about this. We want to convert a word into a list of numbers, right? And the easiest way to do this, if you've learned about a dictionary, for example, an MIT App Inventor, a dictionary does exactly this. You have a key and a value, right? So you put in a key, which is your word, and then it'll spit out the value that's associated with the key, which is the vector that we're looking for. Does that make sense? So if we were to do this, we want to construct a function. A way that we can represent this function is with a table, a huge table. So, uh-oh, this is a bad line. So it's a huge table. Oh wait, it's because my tab is sideways. So we have a huge table, and every single row corresponds to a single word. So imagine that we start with the A's. So, you know, action is an A word, award is an A word, um, accelerate is an A word, etc., etc., etc. And imagine that we have 120,000 of these. These represent the entire English language. So how would we construct this function from word to vector? Well, if we ever wanted to find the representation for a word, we would simply go to the row with that word and slice out this row of this matrix. So this matrix is just a bunch of numbers, right? You know, like I'll just put integers for now. They're usually floats, but it would be, this maybe corresponds to the award. So 0, 1, 5, 6, 2, 9, 8, 4. Action corresponds to 5, 2, 1, 4, 3, 3, 7, 7. And then accelerate corresponds to something, and it's just keep going. And whenever you want to construct a word, then you put it into you look it up in this table. You just go to accelerate. For example, if we wanted to call f accelerate, then we would simply do a lookup. We would be a lookup on the table. So you would go to this row and you would look it up. So this is how you would find the numerical representation for a word once we already know that numerical representation. Does that make sense? And so now we can talk about how we find these representations. Okay, I just wanted to make sure. Does this make sense for how we find it? Okay, great. So this makes sense. So this is how we go from word to vector. But how do we actually find what this big matrix M is? This is a question. How do we define it? So initially, remember that we talked about using one-hot vectors. So instead of having arbitrary numbers here, we would basically be having a bunch of a bunch of zeros and ones. So maybe action would be the one with a one here and a zero everywhere else. Award would be 0, 1, 0, etc. And then accelerate would be 0, 0, 1, 0, etc. And you would just keep going. So this is actually a very easy matrix to construct. In fact, this is just what we call the identity matrix, where you just have ones on the diagonals and 0 everywhere else. Um, Unfortunately, we talked about some of the problems here, right? Because when you do this, when you have an identity matrix, all of the rows of the matrix are independent to the other rows, or are orthogonal to the other rows. So then action would be orthogonal to accelerate, award would be orthogonal to accelerate. Um, and then this would be a problem because if we were looking at the word representation for accelerate, and then we were trying to compare to the word representation for example, faster, these sort of mean the same thing. When you tell someone to accelerate, you want them to go faster. Unfortunately, if we did one hot vectors, then their dot product, or in other words, their similarity would be 0. And this doesn't really make sense, right? Because we want words that are similar to have similar representations. That's sort of one of the ideas that we want to embed into these embeddings. So this is bad, right? Um, so how do we find better word embeddings? I will talk about this in a second. So we actually haven't gotten there yet. But the idea is just imagine that people have already found the right word embeddings. We'll talk about how exactly they're trained in a moment. But imagine that we found the right word embeddings. Uh, you know, we did gradient descent. We trained all of these word embeddings, and now we just have this big matrix of numbers. Then we can just look it up. I think that's the most important part, and I'll talk about training in a second. Does that answer your question? Or okay, cool. Yeah, that's a really good question. Um, Anyone else have any questions about vectors, one-hot encodings, word embeddings? Okay, great. Well, let's move on then. Um, let's talk about how these are actually used in practice. This is going to be interesting. So remember, yesterday we talked about this thing called a recurrent neural network. Um, this is the math that we talked about for the recurrent neural network, and it's really simple. Let's go through it once again. I've omitted the bias here just because the bias doesn't really change anything about what we talk about. We can just add it in whenever we implement it, and this makes it a little bit simpler. But remember our h of t, does anyone want to remind me what this represents? Yeah, exactly. This is what we call the memory, or this is what the RNN understands at each step. So the RNN understands whatever it is that is in this hidden vector at each step. And how do we update this memory? Well, we have three weights. We have WX, HH, WXH, and WHY. This is different notation from what we saw yesterday. I think this might have been WI, this might have been WR, and this might have been WY, but they basically mean the same thing. If you look at this equation, you'll figure out what it means, because h of t minus 1 is the previous memory. So then WHH tells us how much we should remember from the past. And then WXH corresponds to WXT, which is the input. So this tells us how we should update our memory with the new information that we have. And then H of T, of course, is the memory. And so then WY or WHY tells us how to construct output from memory. And this arrow should be pointing towards HY because this is the weight that tells us how to do it. So this is literally all there is to a recurrent neural networks. I think it's a pretty interesting idea. Now, it's really great that you guys remember what the memory is and the whole idea. So, I think we're ready to dive into the applications to NLP. Um, right. So this is a recurrent neural network that's been unrolled. I think this is a really nice representation of it. Again, we have the H's, which are our hidden states. We have any input sequence. This could be a sequence of words like the dog, blah, 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 just as a reminder. And then the outputs, it says optional here, because remember, if we have outputs at every step, does someone want to remind me what kind of problem this is? It's in the format X to Y. What are X and Y? If we have outputs at every single step. Yeah, exactly. This is what we call many to many. And we don't always do many to many. This is perhaps something we might use for translation, but in some cases, we don't really care about anything except for the last output. In this case, that would be many to one. Many to one. Yeah. Um, Great. So this is our recurrent neural network. And we can construct a language model from this recurrent neural network. It looks exactly like we talked about before, but we now have word vectors instead of just numerical inputs. So the example that we're going to be working with here, and this is actually, we'll be killing two birds with one stone because the language model is precisely how word embeddings are trained, but I'll talk about that in a moment. Um, let's just say that we have a sentence, right? The students opened their something. Now, imagine that we wanted to train a language model to predict the next word in the sentence. The students opened their. So naturally, of course, some reasonable words that might come next are books and laptops. Does anyone want to suggest any other words that might be reasonable uh, continuations of this set of words? Yeah, backpacks, right? Or maybe lunch boxes. That makes sense too, because these are students. Maybe they opened their wallets because they were about to pay for something. I don't know. But let's say that we have a language model and we're trying to figure out what the next word is. Now, remember that we talked about, when we talked about earlier, uh, we have these problems, many to many, one to many to one. What kind of problem is this? If you assume that this is like a training sequence and you want one output, what kind of problem is this in terms of the X to Y format? And I'll sort of narrow it down for you. Is this many to one or is it many to many? Sort of a tricky question. Take some time to think about it. Anyone want to guess? You have like a 50-50 chance, I guess, about. Oh, okay. So we have two correct answers. That is great. So this is indeed many to one. You might think that it's many to many because we're sort of trying to generate text, but the key here is that we're not trying to generate text. We're trying to generate one word. So indeed, many to one is correct. So good job on that. Um, so we have this training sequence, right? The students open there, and then we want to predict one single output. So as we talked about before, we allow the neural network to accumulate its knowledge, right? We pass in it updates the hidden state. We pass in students, it updates the hidden state. You pass in opened, it updates the hidden state. You pass in there, and it updates the hidden state. So eventually, at hidden state number 4, you will understand something about the sentence. You'll be like, there are some students who are opening something. And then when you output this weight U, this is equivalent to WY or WHY that we talked about earlier. They're the same thing. If you apply this output weight, you can eventually get out a probability distribution over all of the words in the sentence. This starts from A to Z, and perhaps there are 120,000 of these words in this distribution. But then you look at which activation is the highest, right? Because that would be the one that the neural network thinks is most probable to see. And as you can see, the neural network thinks that books and laptops are really good options for the continuation of this sentence. So this is what we call a language model. A language model is something that models language, and the most popular way of modeling language right now is to use an n-gram training. So what this means is you give it, I'm not exactly sure if it's n or n minus 1, but let's just say you have n minus 1 inputs and you have a 1 output. So in total, this training example consists of n characters. So that's why it's called n-gram. And you might ask yourself, well, why is it that people just seemingly arbitrarily decided that language modeling is best done with n-grams, where a good understanding of language means that you can see some words and predict what's going to come next? Well, this is an interesting sort of almost philosophical question. Like, why is this the task that we use to model language? What I will say is that intuitively it sort of makes sense, at least to me, because if you understand not only the syntax, but you also understand grammar, the structure of the language, if you understand the context, maybe cultural information or just general knowledge about the world, if all of these three all of these three things are necessary for understanding language. Are they sufficient? Maybe not, right? Because when we talk about modeling, we're always talking about simplifying problems down to the degree that we can actually solve them. But they're definitely necessary. Um, they're definitely necessary components of predicting the next word. And if they're necessary components of both predicting the next word and understanding language, we might think that doing this n-gram training is a good proxy for really being good at language, because somebody who is good at language will definitely be able to predict a reasonable word for the next word in a sentence. It may not be sufficient to say that they're good at language, but somebody who is good at language is definitely good at doing this. So humans are just like, yeah, this is good enough. It's a good enough model for language, and we'll just roll with it. So I promised to you before that we'd talk about how exactly these word embeddings are trained. And in fact, it is literally just using this language modeling task of n-gram. But how do we do it? Well, here is how. You can think of these things as training pairs. Does anyone want to remind me what vocabulary we use to describe this and this if it's a training pair, an X and a Y? So what is this at the bottom here, the X's? What is the technical lingo that we use, we introduced
Input,
maybe on day one? Yeah, so it's an input, but yeah, that's pretty much it. Like, it's an input, but
parameter.
we call them features.
Oh,
Be
okay.
careful about calling it parameters, because remember, parameters are things that are learned by gradient descent, like the weights of a model.
Oh, okay,
So
okay.
yeah, yeah. Um, but these are features. They're inputs. Great job. And this is a label. What you're supposed to see. This is a label. And what you basically do is you feed these inputs into the model. It runs its forward propagation and it spits out a value. Initially, this is the Y predicted. Now, initially, this value could be pretty bad. Maybe it says the students opened their, I don't know, they open their pens. Like, you don't open a pen. That doesn't really make sense. So initially it says it opens their pens, but when we do gradient descent, we're basically saying, you said that it was going to open their pens, but in fact, my label says that they should have opened their books. So there's this difference where we can construct a loss function, remember, from maybe lesson 1 or 2. You have Y predicted and Y true, where Y true is the label. And then we want to minimize this value based on changing the weights, changing the parameters. So when we run this minimization, we're not only running minimization over W, H, W, E, and U, which are the weights that control the neural network. Well, yeah, not only those, but we're actually running it over the embeddings too. So the specifics of this you won't necessarily have to understand, but basically you can ask the question to this learning algorithm. You can say, how to modify embeddings to lower the loss or the error. This is the fundamental question that you can ask. And remember, if you remember, this is good for you, but you are in no way responsible for this. This actually corresponds to a gradient or a derivative, which you probably haven't studied yet, but this question corresponds directly to this idea of taking a derivative and running gradient descent by showing it an input, getting its output, and comparing it to the correct answer. And you can be like, model, you're very bad. Please change yourself to be better. And it can modify anything that's a parameter here. So just as a concept check, does anyone want to list out all of the things that gradient descent can change right now? Yeah, definitely. It can change the parameters. So do you want to list out the parameters? I think as a clue, there are 4. We're not exactly 4, but there are 3 and then plus a whole class of them. But yeah, I'm looking for 4 parameters that when you train a language model here with an RNN, that gradient descent can update. Okay. So very good. I'm seeing some good ideas in the chat. The weight is one, I think. This is correct. And how many weights are there in this model? So remember that we have a recurrent neural network, right? Nothing has changed from a recurrent neural network. What are the parameters that we can change here? Can someone list them out?
The W's?
Yeah, exactly, right? So you have the W's. And I bring this up because you should be able to see corresponding W's in this image. W, E, W, H, and U, right? So in fact, these are the parameters that are in the RNN. So when you train a language model, you not only change the embeddings, but you also change the weights as well, of course, because you're trying to learn a task and you need weights to learn the task. But in addition to these 3, this is something that wasn't in the original RNN. You can also modify the embeddings, which are the E's. So the E is actually what I was talking about to the person who asked how we train these things. The E actually corresponds to this big matrix. I called it M, but this also should be, in the other slide, it's called E. It's this big matrix E, where E is whatever you look up from the word. So in that example, it said the students opened their, I think is there or something. So then you would do the lookup in this matrix E of the, and then you would do the lookup in the matrix of the students, and then it would look up opened, it would look up there, and you would update this matrix, basically changing the specific rows that correspond to these words. You would change the specific rows that correspond to these words, and how you would change them, the gradient descent algorithm would figure out. It basically, again, it asks how to modify the embeddings to lower the loss or the error. So all in all, there are 4 parameters that we're changing. The big output matrix, the big matrix that tells you how you should remember previous states, the big matrix that tells you how you should remember the new inputs, and then finally, the big matrix that defines all of your embeddings. So you can update all of these, And the magic thing is that after you do this, your not only will your weights be pretty good, your embeddings will also be very good because you've seen a bunch of different words from the English language just by looking through all of the internet archives or whatever, and you have found embeddings for each word that that are very good at, in synergy with W, E, W, H, and U, are very good at predicting the next word. And then the assumption that people make is that if this happens, then you have a pretty good prior for other language modeling tasks. And in fact, this is true. So these embeddings that people get from doing this what we again it's called an n-gram task again and again, n-gram, the embeddings that people get are super, super good for learning other tasks, the tasks that we talked about at the very beginning of class, including all of these, like all of these classification tasks and even these question generation, stance detection, translation. These embeddings are very good for all of these. So a very interesting idea that helps us achieve this cool thing called a word embedding, which has all of these interesting properties that we talked about, like vector addition, this sort of information memorization, and things like that. Does anyone have any questions about language modeling with this n-gram task, or how these embeddings are computed? If you're good, just put a thumbs up in the reactions. And then if not, feel free to drop a question in the chat. Okay, great. Looks like we're ready to move on. Um, the other thing that I wanted to mention is that this U, we already talked about this pretty extensively before, but the output is task dependent. What this means is that the task dependence, what this task dependence applies is that you can actually swap this out. You don't necessarily have to predict the next word once you've trained your word embeddings. You can swap this out with any other task. So you can look at the probability that a sentence is toxic given these sentences. So if you saw, this random sentence on the internet, it says the students opened their. This is a pretty harmless sentence. I'd probably think it's non-toxic. So then once you saw the entire sentence, or maybe this whole portion of the sentence, then you would probably say that it's non-toxic. And so the whole point of this is that the U matrix is dependent on the task. You can change your U matrix to whatever you want. In this case, it's predicting the next word, or in this case, it would be predicting the toxicity of a sentence. Of course, then you could do uh, a whole slew of different things, just whatever you would need to do with your RNN, you could do here. So um, this section will begin the discussion of some applications of RNNs that are quite interesting. So the first one is part of speech tagging. This is like a very nice example of a many-to-many task, where for every word you want to predict its part of speech. So this is your noun, this is your verb, action verb, this is another noun, etc. So this could have lots of important applications for a variety of NLP tasks. There's also sentiment classification. Of course, we talked about this before. And there's another interesting thing that we should mention here, which is that your encoding doesn't really have to be taken using the final state, because if you imagine that your sentence is super, super long, you might lose some information at the very end that you forgot from the very beginning. So one way that you can fix this is simply just to take the average of all of the embeddings all the way from H1 all the way to HT. So this would be sort of 1 over T sum over all i's HI. This would be your word embedding. This usually gives you better performance because it allows you to memorize things from earlier. And then you would simply just output your classification based on this final encoding. It would be like, overall, I enjoyed the movie, so then this would be positive. And in this case, we talk about a lot of different tasks that I won't sort of talk about too much. Like translation, we talked about this sort of yesterday too, where you feed it an input sentence and then you ask it to start generating things based on this hidden state that it got from the encoder, and then you can decode it. So whatever this says looks like it might be a French sentence. It'll be translated into English using "he hit me with a pie" or something like that. Cool. So does anyone have any final questions about how RNNs work, or how they can be applied to NLP? Because otherwise we can start going into transformers, this new cool technology. Okay, great. So let's talk a little bit about transformers. I won't be covering this in nearly as much detail as I did with RNNs, but I thought that you all should know about it because these things are taking over NLP and people are very interested in them because they're much better at a lot of language modeling tasks and even sometimes vision tasks than your regular RNNs are. So what is a transformer? Well, it's basically another way to deal with sequential data. So it is not quite a sequential model in the manner that it's recursive. You're not applying, different inputs and then recursively updating a hidden state. That's not what transformers do. It's more similar to a regular neural network. It is very similar to just an artificial neural network that we talked about before, where you have a bunch of inputs, you have some processing units, and then you get an output. But at the core of these transformer models is this idea of attention right here that you can see. And we won't be talking too much about the attention layer, but you can just think of it as a modified ANN that has these cool things that enable it to learn very interesting representations that are not quite dense. So it's not exactly a fully connected artificial neural network. It's a little bit different. But ultimately, what you get out of the attention layer is this very interesting property that we'll talk about soon. But if you've been like sort of following over the course of this course, we can already start to understand transformers just by looking at this picture without really understanding what's happening inside the transformer, right? Because at the very input, because you're dealing with text, you need to put an embedding here. So maybe this would be the dog traveled west or something. Of course, then you would put it through an embedding layer. So then these would all become vectors, vector 1, vector 2, vector 3, etc. And then you would put it through a transformer encoder, where this is basically, you can think of it as a huge neural network that is performing some transformations on the input. And then ultimately you get out an encoding, right? An encoding is whatever the computer understands about the model. It understands that this sentence is about a dog traveling west. And then you can apply another fully connected layer on top of this to do classification. So in fact, what I've described here sounds very, very familiar. It just feels like a big recurrent neural network that's been unrolled, except there's this weird new internal computation structure here called the transformer. So let's talk about what the transformer is. The transformer's architecture looks like this. Don't worry about what all of these things on the inside mean. They're just a bunch of different operations that help us model the way that English works. A lot of people actually think that transformers are arbitrarily designed, and I think this might be true. But there's this whole system of things that we'll discuss what it looks like in a second. There's a whole system of computations here that transform an input into an output. And you can think of each of these as just not exactly extracting features, but just taking words and transforming them into increasingly abstract representations until the very end, where it sort of encodes everything that you need to know about a neural network in a very small, low-dimensional vector. But at the core of transformers are this thing called attention. There was a paper published maybe 4 years ago called "Attention is All You Need," and it was groundbreaking because it said that we don't actually need recurrence to solve these NLP problems, we can use this thing called attention and just solve everything with it. So what is attention? Well, these are the equations that govern attention. We won't be talking about these too specifically because this was copied from a presentation that I made to another group of people. But this is what we should really be focusing on. And I think this is very interesting. So what is attention? Attention basically operates on the idea that a word should be represented by a linear combination of some other words. So what does this mean? Well, when you think about a word, right? If you think about the word nurse in this sentence, let's just read the sentence first. The nurse examined the farmer for injuries because she. It's an incomplete sentence. It's sort of like the first part of a sentence. To understand what nurse is, you might need to understand a bunch of different things because you need to understand that the nurse is has a relationship with the farmer, like a relationship as in they are two entities in the same sentence and they are somehow interacting with each other. Because the nurse is examining the farmer, the nurse might need to look at the word examining because the nurse is examining someone. This is the action verb, and the farmer is receiving the action. And then what are you examining him for? You're examining him for injuries because the nurse is good at examining someone for injuries. So et cetera, et cetera. Fundamental idea, you need to look at other words when considering a word, considering the meaning of a word. So every single word can be represented as a sort of a combination of all the other words. And this is exactly what attention does. And I think this is particularly interesting in the case of in the case of gender here, resolving the gender. If you notice, we left the word she a little bit ambiguous, right? Because the nurse examined the farmer for injuries because she, if she represents the nurse, then the rest of the sentence might read, the nurse examined the farmer for injuries because, she was trained to do so. This would imply that she refers to the nurse. But if we said that the nurse examined the farmer for injuries because she was in a lot of pain, then she would actually refer to the farmer. So there's a lot of ambiguity in language. This is what we talked about at the very beginning. And looking at attention can help us decipher what is happening. Because attention is if you look at what the attention is doing, if we look at the left and the right graph, on the left graph, she is attending highly to nurse. This big square here means that she is looking very closely at the representation for nurse. This is very striking, right? Because in a model, there is a sense of gender bias that statistically nurses are or nurses are more likely to be women. So then when you see a word she, then you might associate with a nurse. And then statistically, maybe farmers are more likely to be men. So then you would associate a he with farmer. And you can see that by training on a big on a big data set, this model has learned this gender bias because whenever you construct your representation for she, it's saying that the nurse is a very big candidate for it should influence the representation for she a lot. And this tells you that it's associating the nurse with the she. Or in this case, after we've intervened in the model, we've sort of gone in the weights and we changed something, we can get she to attend to farmer. And what this means is that it thinks that the farmer is now the woman. So attention is basically about trying to figure out what words are important for formulating the representation for a word. Um, and ultimately, you just keep doing this again and again. You take all the most important words that we're attending to and you add them all up. So in this case, you can see that she attends largely to nurse. It attends a little bit to farmer. So we might take in a little bit of farmer and it doesn't attend to much else. And then so to construct the representation for she, you would basically add the representation for nurse, and then you would add the representation for farmer. Farmer, not the A, farmer. And maybe you would weight this one, weight less. And then you would just keep doing this again and again. You would represent each word with the other words that are most related to that word. You would do this a lot of different times, maybe let's say 48 times in a big model like GPT. And then eventually you get out an encoding. This encoding represents everything that you need to know about the sentence. It's a very small dimensional encoding. And this represents the entire sentence. And then you can do whatever you want with it, including doing decoding, you can do classification, and et cetera, et cetera. So I know that a lot of this sounds a little bit hand wavy because we weren't able to talk about specifically what all these components are or what this math means. But just take away this. Transformers are very, very similar to artificial neural networks in the manner that it's a fixed input size. You just feed everything in and you get an encoding out. But how we get this encoding is kind of interesting. It's called a transformer encoder. And it's based on this idea that every word should be some combination of the words that are important to it. And how do we define how important a certain word is to another word? Well, that's for the model to learn through backpropagation, through gradient descent. But ultimately, after you train the model, by looking at the attention maps, you can sort of see what the model thinks is important. It thinks that the nurse and the farmer are important to she because this resolves the co-reference. This is a problem called co-reference resolution. It resolves the co-reference to nurse, which means that she should tend highly to nurse and a little bit less to farmer. And because it thinks this, it's going to construct a representation for she with a lot of nurse and a little bit less of the farmer. And it'll just keep doing this. It'll keep refining these representations again and again through all of the layers of the model until you get a representation that combines everything into everything. So that's self-attention, and those are transformers. Does anyone have any questions about this? Okay, great. All right. So this pretty much wraps it up for the theory that we're going to cover today. So just as a big recap, we first talked about NLP tasks and why it's hard, different tasks like classification, question generation, etc. And then we talked about this big problem that words are not numbers, are not numbers. So we need to convert words to numbers using something called a word embedding. These word embeddings basically take words, and you represent them as numbers. We initially explored this idea of one-hot encoding, which is just taking everything, setting it to 0 except for one thing. But we figured out that one-hot encoding is bad because there is no similarity, no notion of similarity. And then the other way was, remember, we trained it called an n-gram training procedure. And what we did was we trained a model to predict the next word in a sentence. And we made the assumption that if a model was to do this well, then it had a good grasp of language. And this would help us generate all of these maps from words to numbers. This was what we called the word embedding. So then finally, we discussed how RNNs work in NLP. We covered a couple of example tasks. We showed the architectures for them. And then finally, before we talk about transformers. Transformers are better or in general than RNNs. And the big idea here is this usage of attention, where the fundamental concept is that every word should be represented by a combination of others. So your model would basically learn what words are important to formulating what representations to solve the task correctly. And eventually we got this very nice interpretability map where we could see that we're formulating the representation for she highly dependent on the representation for nurse. So we can make the connection that the the model really thinks that the nurse is the woman in the situation. So not only does this give us a very good representation at the very end, but it also allows us to interpret what the model is thinking. So this big summary is everything that we covered in terms of theory, sort of. And now is the time to talk about application and how we can implement some of these cool things in MIT App Inventor. Today, once again, we'll be using an API because a lot of these models are super, super complicated. And once you get into high school and once you start programming in Python and once you learn things like TensorFlow and Python and PyTorch, we will actually be able to implement some of this. This slide is actually from a summer camp that we ran last summer, where the students who were in high school, they built an image captioner from scratch using TensorFlow. Very interesting, quite a difficult thing to do. But today, we're basically going to use an API and we're going to integrate it with MIT App Inventor so that you can take pretty much any image that you want off the internet and we can caption it and see what's happening. That's going to be our lab project. And then for your homework project, you're going to be following some instructions to build a chatbot. So remember how I talked about the chatbot being a super, super difficult problem to solve? Right at the very beginning of class, we were talking about how chatbots are very difficult. Facebook bots, any chatbot is similar, but you're going to be building one, and this will give you some insight into how difficult it is to get a chatbot to really pretend like it's human, and you'll see what you can do to tune it and see it work around in MIT App Inventor. All right, well, sounds great. Let's dive into the lab now. Just give me a couple moments to pull up all of the things that we need. And in the meantime, feel free to start a new MIT App Inventor environment. Today, we're not going to be starting off from any template. We'll be building this all from scratch. All right, so let's create a new project name. We can call it, I don't remember what lesson today was. Today's lesson 5. So lesson 5, image captioner. Whoops. Captioner. And before we start coding the application, I just want to show you the API that we're going to be using. It's yet another one from Deep AI. You might remember this from earlier, or maybe not. We used the GPT one in the past. Cast. But the DenseCap API is a neural network that somebody has hosted that enables you to caption images. Now, the way that it works is you either have to do a file upload or Google search some images. I think I'll just do some Google searching. Does anyone want to suggest an image that I should caption? I don't really know what I should caption. Interesting photos. Okay, maybe we'll caption this thing. Basically what you do is, oh, let's try this one. You right click, you copy the image address, and you can put it into the DenseCap API. You paste it here, and it'll run it through its neural network, and it's going to return to you a result. Now, I'm going to post this link in the chat so that you can play with it if you want yourself too. But as you can see, it is not perfect. It thinks that there's a window that is white down in the corner. It thinks that the rock that this cat is standing on is an umbrella. Here, it's a little bit more correct. There's a top in the rock. The mountains are in the background. This is really good. Sky is blue. That's great. Mountains are in the background. I see something about a cat, so that's great. As you can see, it's a little bit hit or miss, the reliability of this image captioner. But I think it's still quite interesting that you can take any image, and not only is it going to give you one caption, it's going to locate all of the parts of the image and caption each of the specific ones. And maybe half of these are good captions. This might be a little bit of a more difficult image though, because it's sort of low resolution. There's a lot going on. What if we have this? Well, I think it's ice cream. Oh wait, whoops. Copy image address. So yeah. Ooh, what is happening? The picture is white. You know, you're not wrong. The flowers are yellow. These aren't quite flowers. It doesn't really say anything about an ice cream cone, which is a little bit disappointing. Uh, but yeah, as you can see, we're just messing around with the API. It seems to do pretty well. It's not perfect. Photos of flowers. We can also do this. Um, let's see whether the model can figure out what's going on. Okay, great. So it doesn't say anything about sunflowers, but it says the flower is yellow, the flowers are yellow, the fence is green, not quite. A clear blue sky, this is great. Flowers yellow, the flower is black, whatever, whatever. So I will stop wasting your time messing around with this API. As you can see, it works, it's not bad, it's not perfect, but this is what I was talking about earlier. Like image captioning is a very, very difficult task, and I think the fact that we can do this already is pretty amazing. So let's try to explore the API. So the API is a little bit complicated because we'll have to do all of this curl stuff. But let's go ahead into our MIT App Inventor and let's try to build an app. So this API requires you to either basically it requires you to specify an image URL. And this is a problem if you want to take your own pictures. So let's just allow users to enter their own URLs into this app. So we'll go ahead and create a horizontal arrangement that contains a text box where someone can put in a URL and a button. We will make this horizontal arrangement fill the width of the parent. We will make this text say go, or the button text say go. Let's rename it to button go so that it's a reasonable. Then we can go to its width of the text box. We can make it fill parent so it looks nice. And I think I will set the width of this this button to maybe 15%. And we can change the hint to say type image URL here. And let's go ahead and connect our AI companion. And just to make sure that everything's working properly, let's scan this. So note that if you're having issues with connections, you might want to try the legacy connection. I was having issues earlier. Unfortunately, MIT App Inventor is sorting through some problems right now with their thing. But there you go. See, we can type in a URL. We can click go. Nothing's going to happen so far. But you know, we're off to a start. We're off to some start. All right, let me just split my screen this way so that you can see what's happening on my phone. All right, so we have this. We're going to want to display our image so that we know that whenever somebody copies in something, it'll be there. We can paste in an image, and we can also paste in a label. This label can say your image or something like that. Now your image is going to be here, and let's also put another label which says caption candidates, because remember this caption this API is going to return us a whole lot of different captions, like a whole bunch of captions, and we don't really know what to do with them. We'll just display all of them all at the same time. So for this one, I'll just make the text nothing, and let's call this label outputs. Always remember to name your components to name them something meaningful if you're going to be interacting with them. So this is called like image display. Now these labels that I don't interact with, I don't really care what they're called, but this text box, we'll call it input URL or something like that. So we have our interface set up. There are a couple of things that we need to import. We of course need to import the web because we're going to be using our API. I will always import my trusty notifier because it's good for debugging, I guess. And right now we're ready to go to the blocks. So what you need to know about the blocks is that there's this thing. You have to do curl. We don't even know what curl is yet, but this is what we call a JSON API. I hope many of us have seen these before, but basically, the idea is that you have this URL and you want to put it into your web. And then every time you want to ask for the labels of an image, you're going to call post. You're going to post the URL of the image, and you're basically asking the server, hey, I want your information. Please classify, please generate captions for this image. And it'll do it and it'll return it to you. So let's go ahead and do this. We first want to do button go. When button go.click, we want to, let's say, set a variable here. Let's create a new local variable called, what do we want to call it? URL. Just call it URL. And what do we want to set it to? We want to get the input URL. So we want to get the text from here. All right. So once we do this, we have our URL. What do we want to do? Well, I guess the first thing is that we want to set our image display. We want to set our image display picture to this. Let's say that we want to get URL. So we set the image display picture to URL, then we should be able to get the URL. Well, how do we do this? Well, then I'm going to have to get a URL. So let's try to find an image. We'll like find flowers. We can go to images. We can find some flowers, I guess, and we can. I think there should be a way to copy the link address. Copy. There we go. Wait, I don't know if this is gonna work. Yeah, I don't think this is gonna work. Well, we need another way to copy the link address. Or maybe we can find dogs. I think we can visit. And then, there we go. Wait. Share image, I think. Maybe. Okay. This is sort of difficult. Okay, you know what I'll do? We'll just go to a website and we'll just like dogs, images, and then we will copy image address and we will just set the URL to this temporarily for debugging. And in the future, when we have our app, we will just swap it out. So if I click go, it'll put the image of the dog here and it'll say your image. So this should be working correctly now. And the next thing that we need to do is generate some caption candidates. And this will be where we use our web. So the first thing, if you don't remember how to use an API, we first have to set the URL of the web to the API endpoint. So I will copy this and I'll also send it in the chat. So you should be able to see this in the chat. Well, we're going to set the URL to this. And the next thing that we need to do when using an API is that, as you can see, this -h here represents a header. And a header is where you need to pass in an API key. Remember that an API key is something that people use to verify that, it's like a verification tool. They want to verify your identity to make sure that you're authenticated to actually use this API. So we need to create some headers. I'll copy the API key. You should go to this website that I sent in the chat to copy your own API key. I think they're all different based on your IP address. But you're going to want to set your headers, set your request headers in the following way. It is going to be a list of things, and you want to make a list of a list because your list is going to be the list of the API keys, but then each element is going to be a list where the first thing is whatever it is, like this is the API key, and the second thing is the value. This is like the key and the value. So this will be your request header. And then you're going to want to go to web and you want to post your text. When you call post, you're basically saying, let me send you some information. This is the information that I want to use, and please give it back to me when you're ready. So then you're going to go to text and you're going to be like, let's call it join. We're going to want to join image because right now see that it says when you pass in your text, you want to pass in the image equals and then your image URL. So then you're going to want to get the URL and put it here. Then when you post the text, it should get the URL. So this is all we need to do when we do button.click. Does anyone notice anything missing? Are we done here with our application? Will it work if I click go right now? Right, so it won't work, right? And so do you want to suggest a solution, or what is wrong and what do we need to do? Yeah, exactly. So you're going to need to get an output, right? And currently we're not doing anything to intercept that output. So we're going to need to do when web.got_text, and we're going to want to see what the response content is. Response content. Initially, we don't really know what's going on. So all we should do is just set it to the label output just to see what happens when we do this. And if we click go, it's going to do some things. It's doing something, and it's going to output this strange looking thing. There were a couple of things that I noticed there. First of all, you can tell I can't scroll. You can tell that I'm scrolling on my phone, but I can't really do anything. This is bad. So we need to go to our designer and go to our screen and make it scrollable so that the next time we do this, it's going to allow us to scroll through all the captions. Second thing is that in between the time that I clicked go and in between then and the time when we actually got the response back from the web, nothing really happened. And I was wondering whether the app was broken or not. So one thing we can do is immediately after we post the text, we can set our label output to something along the lines of loading. So loading. And what happens now is if I click go, it'll say loading until we actually get the response back, and then it sets it back to the actual response. So this is a much better system for keeping people in the loop as to what's happening. All right, so we're pretty close, right? We've got the bounding boxes here. It's even giving us the coordinates. It's giving us some confidence, and it's giving us a bunch of different possible captions. Now, there is one possibility, right? Given this API, if you had a tool that could help you draw rectangles around this box, you could actually see what was happening. You could see, you could actually draw the rectangles and see where the model was making the predictions. And if we put this in here, we'll actually be able to see it. Unfortunately, MIT App Inventor does not make this possible. I looked into this, and it's possible to do some really jank workaround with canvases and sprites where you upload a picture of a rectangle and you squish it around to make sure that it fits. But then I eventually decided that this would be too clunky and it's going to be a little bit wonky with the sheer number of things that are on this board. So so we're just going to list out all the captions, all the best captions. Now there's a question in the chat. When I went to web and set request headers, why did I have to make a list inside of another list? This is a really good question. So remember that headers, we don't have to just have one, we could have multiple headers. Like in this case, we didn't have to specify other headers, but we could have needed to specify, what type of input we were giving it. This is the type of input. We also could have, submitted another header based on the application, your identity or something like that. These are not concrete headers, but this first list is a list of all the different headers. But to actually represent a header, you need a list because you need to tell the API, this is a header that contains the API key. That's what the first index is. And then it tells you the actual value. So you can think of this as a key and a value. So every single header is represented as a key and a value. And as a result, you need to make a list for each header. But then the first list is just the fact that you could have many, many headers. Like there's not just one such header. You could have different kinds of headers. Does that answer your question? Okay, great. Cool. So Again, we could be drawing rectangles over the dog thing, but it's really just a hassle, and it won't look great because of the number of boxes here. So all we'll do is just simplify this thing down. We just want all the captions out. So how do we do this? Well, our response content is encoded in dictionary style. So we're going to want to go to our web, and we want to JSON text decode with dictionaries. I think this is the best way to do it, because then you'll get a dictionary out from the response content, and the dictionary, we can index it with keys and values and things. Uh-oh. It looks like you're enjoying our API. Want to keep using it? Sign up to get an API key that's as unique as you are. It's free. Okay, as you can tell, I've used my API too many times, and it's now yelling at me. So unfortunately, we won't be able to continue because then our API is broken. So I can send out the solutions once my API has been back. They probably like said that I could use it 10 times a day or something like that. But feel free to consider this homework. This should be pretty simple. So if you create a dictionary, and let's set it to a variable, and we can call it response. Oops. So you can call it response. Response dictionary. And you set it to this, then you can set your label text to to just a list of things, or a list of these captions. You don't want to have all of those squiggly lines, the curly brackets, all of those things. You just want to print out a bunch of caption candidates. So like all the possible captions that might be good candidates for things. And then, of course, if you actually implement this, you should swap out the dummy URL that we use for testing with the actual URL. But feel free to treat this as an exercise, sort of like a pre-homework assignment if you want to. If you don't want to and you just want to leave it as brackets, that's also totally fine. But I think it's going to be a good opportunity to practice your coding skills. Like you should be able to do this in 5 minutes, maybe on your own time. So just treat this as like a coding practice thing. But yeah, so this is a really cool example of using NLP in conjunction with computer vision to solve a really difficult task, which is just give a computer literally any image in the world and it can generate a sentence that describes what's happening in that image. I think it's quite cool. So yeah, and as you can see, we are continuously harnessing the power of APIs. And the more that you work in this area, the more you'll realize that APIs are super important, because you don't want to reinvent the wheel every time you want to do something cool. There are so many APIs out there that implement these AI methods that we're talking about. And first of all, well, you already know how they work now based on the technical content that we've covered in this class. And also because other people have been so generous as to release their API, you also know how to implement them in your applications. And I think this is super powerful if you're ever looking to build projects that can solve real problems, or you're doing a hackathon, or you're building a science fair project, or whatever it may be. Definitely harness APIs. They're great, and they're really fun. So yeah, that concludes our lab today. I'll post the actual solution on the master document later tonight, and you can feel free to take a look. And also in your free time, feel free to implement this thing where you simplify it down, you cut out all the unnecessary um, unnecessary stuff, and you just keep the specific captions. Just put them down in the labels. So yeah, your homework tonight will be posted also on the master document later tonight. But the idea is that you'll be building a chat bot that can chat with you, and you know, that should be interesting. And then finally, I haven't forgotten, I will look into this problem with the speech recognizer thing, and I will post a message in Discord about it once I figure it out. Does anyone have any final questions or anything before we end for today?